Hello, my name is Kristine Van Natta. I work for Thermo Fisher Scientific. I'm here at ASMS 2011 in Denver, Colorado, and I'm here to tell you about our implementation of high-resolution accurate mass for the analysis of synthetic cannabinoids in human urine. The background behind this is for many years the pharmaceutical industry has been synthesizing synthetic cannabinoids. These are cannabinoids used to mimic the natural cannabinoids, tetrahydrocannabinol, the active compound in marijuana. Why are we trying to synthesize synthetic compounds to mimic marijuana? Well, they have been trying to mimic the beneficial effects of anti-nausea for cancer patients as well as the pain-killing effects while eliminating the psychoactive effects. Most of these compounds never went anywhere and just stayed without a patent in the pharmaceutical industry. The designer drug market has now found these compounds and has started marketing them as legal highs as alternatives to marijuana. The DEA has gotten wind of this and has done an emergency scheduling of several of these compounds to make them illegal. So now methods are needed to identify these now illegal drugs in human urine. The two compounds I'm going to be focusing on are JWH-18 and JWH-73. As you can see, these two compounds are very similar, differing only by being a pentyl chain versus a butyl chain. In human urine, research has shown that the parent compounds are not seen. Instead, the hydroxylated and carboxylated metabolites are the compounds that are seen in human urine. Since these compounds are so similar, by the time you hydroxylate one compound and carboxylate another compound, you will see that in this case, their masses are quite similar. This makes separating them by their mass rather difficult. You can separate them either chromatographically by time, but once again, since they are so similar, they elute at similar retention times. You can separate them by parent mass, which as I just showed you, the difference is very small. Or you can separate them by fragments in a fragmentation instrument, a triple quadrupole or some sort of trap. However, once again, since these compounds have such similar structures, they fragment to very similar ions, and fragmentation is not an easy way to separate them. Using our high-resolution accurate mass instrument, we are able to separate them even by these very close masses. Here, I have a chromatogram showing the 18 and 73 hydroxy and carboxy metabolites, as well as a deuterated carboxy internal standard. And you can see with our 3 ppm mass windows that the two compounds that we were worried about being so close in mass are adequately separated. To show this on a one-to-one basis, if you will, here is a blow-up window of 73 carboxy with a 3 ppm mass tolerance, the 18 carboxy with a 3 ppm mass tolerance, and a mass window with 100 ppm mass tolerance showing that the two compounds are not well resolved chromatographically, but with the smaller window are resolved by mass, and that also we are able to screen out an endogenous interfering peak. With this high resolving power, we're able to have a short chromatographic run of only 5 minutes. If we had to separate these two compounds chromatographically, up here we have an example of that, where it would require a much longer run of 8 to 9 minutes to separate these same two compounds from what now appears to be two endogenous interfering peaks. In conclusion, we have developed a method to quantitate these four metabolites down to 5 nanograms per mil in human urine. Further work we are planning with these compounds is to optimize the hydrolysis step, as these compounds are excreted as glucuronides in human urine. If you want any more information on this or any other Thermo Scientific product, please go to thermoscientific.com. Thank you for your attention.